Hello friends, today I'm going to talk about Leetcode 1423 maximum points you can obtain from cards. The problem is that there are several cards arranged in a row and each card has an associated number of points. The points are given in the integer array card points. In one step, you can take one card from the beginning or from the end of the row. You have to take exactly k cards. Your score is the sum of the points of the card you have taken. So the input is the card points and the integer k. The output is the maximum score you can obtain. For example, here we have these card points and the k is 3 times you can operate. So you can take 3 cards and output 12 because you can take the first one or one, but which one is we don't know. So we can choose, for here we choose first one or second one, doesn't matter, and then we we have to choose the second this one, and then take 6 and then 5 to figure out to find the ultimate score. And for the example 2, we can see that we can take any of the 2 and 2 and get 4 and so on. So the problem is that we have, for example, we have the 1, 2 and 3 and 4 and seems obvious that we can take the 2 first, and for example k equal to 2, and we can take 2 4 first, and then we take 3, right? We get the answer 7, right? This is the optimal answer. And for example, if we have the example of the 3 2 3 4, we also take this 4 and 3, but how about if it's 3 3, now here maybe we can use 4 and 4, and which one should we take? Because if they are equal, we don't know which one to take. For example, if we take a random one, if we take first 4, if we take first 4, then we can take the second 4 again, so we get the 8. That is optimal, right? It seems that we can use a greedy way to optimally select the select one from the beginning or from the end. If the beginning is smaller, then we take the maximum of the beginning and then the end. If they are equal, we can take a random one. So is this greedy way is optimal, is a solution, optimal solution at least? How do you think? I think it's not an optimal solution, because let's give a counter example. The example is 5 1 6 4. Let's if we use the k equal to 2. So how do we fetch this? If we fetch 1 5 and first 4 5 first, right? And then we fetch 4 first, second as the next element, then we get the answer is 9, right? So is this 9 the optimal solution if we use this greedy way? No, it's not, actually not. It's the optimal solution is 6 plus 4 equal to 10. So we have to fetch 4 first, then we fetch 6. So in this case we can see that the greedy way is not an optimal solution. So for this question, so we can use a dynamic programming, because if they are equal or not equal, we don't know which one we should pick. We don't know whether we need to pick the smaller one or the bigger one. So we can use a recursive way to figure out both ways and recursively to until to the end, and we pick the one of the best one. So the idea is that, for example, we have the 1, 2, and 3, 4, right? And after we pick one number, we pick 1 or we pick 4, and the last element should be the 2, 3, 4, or if it's 1, 2, 3, right? And then we do a sub problem again. This is a sub problem of this big problem, and this sub problem has also have optimal overlapping substructure, so it can solve with a dynamic programming idea. So it is easy to come up with a dynamic programming with memorization. If you are not familiar with memorization, you can watch my other video about the algorithm on dynamic programming section. I have a separate videos to introduce how to solve problem with dynamic programming, and if with this dynamic with memorization is like easy to come up with a top-down method. So we can define a dynamic function helper and the points array, and also the index I and index j, and current the k so far, and the memorization we call it dp. And first we construct some base case. Let's consider later. And what is the recursive function here? The recursive one is we fetch from the left, so we get the points I, right? And then we add the rest answers. That is, we call the rest answers. The rest points, that is, we should imply 1 by I, and also k should be -1. And if we fetch the end, that is we fetch from the index j. So we have to add j by 1 only, and then we have to return the max of the left and right. So this is a recursive way how to call this. And next, what is the base case here? And the base case is critical here. Base case is that because we use index I and j indicate the index from the left and the index from the right to left. So, and if the k, one is the k equal to 0, we return 0. And the other case is that if the I and j is to the end, so we do not need to calculate again. And the other case is, I think, is that if it's I equal to I bigger than j, and we return 0. Otherwise, we continue to this function and find out the maximum point. So this is the core idea of the dynamic programming. And then because this is as first solution, because we actually has another solution. A second solution is we can transfer to this problem to another problem and use a sliding windows to solve this problem. So what is another problem is that because we can see that we have to find the maximum points from this color points, right? And we can get 1 and this 1 and 1. And because we fetch from the beginning and the end, so the rest array that are the rest elements that are left must be a continuous subarray in this original array. So let's consider for example here we like 1, 2 and 3 and 4 and 5, right? And if we fetch the 1 and k equal 2, we fetch 1 and 5, we get 2, 3, 4 and left. So this 2, 3, 4 is a subarray in this array, in original array. And if we fetch 1, 1, 2, we get the 3, 4, 5. It's also a subarray. If we fetch the 4, 5, we get the 1, 2, 3. This is always a subarray, so we can find that and it is true for any cases. So this problem is transferred to that find a subarray with minimum sum. Because it's a continuous subarray, so we can use a sliding windows, use left point and right point to traverse. It's also another 2 pointers. How do we use a sliding window? And let's consider, for example, here that is we have the 1, 2 and 3 and 4 and 5 and k equal to 2. For example, we start from L is from the index 0, and then we traverse the index R only until the number of elements between these windows L and I is 1 more bigger than the k. This here is 3. Only is 3, then we need to judge whether the current sum has the previous sum has whether has we have to get the current sum between this sum of this L to I, and this is the current sum, and we have to update the current sum. So the final answer is we get the minimum sum and minimum answers and this and current sum. If only the L and I has the same number as the k, and if it's bigger than k, and if it's bigger than k, here is equal, and if it's bigger than k, we have to shift L plus 1. That is the core point of the sliding window, so we have to shift for L plus 1 he- now here we have to shift L here, and we have to delete. Oh. Something is wrong, cannot delete this. Now this we have to delete this, and then oh, I get it. Can only and after that then we can see that we have to shift R again and judge this one. If L if the L and R has distance bigger than the K, when we shift L again, and then we shift again as with R here, and then with L. In this way, so we can find the minimum sum. Let's explain with the code more. And here I am only to write the second solution, that should find the minimum subarray with array length should be the current m points car points minus k. So we have first get the m points, and also the minimum windows for subarray is m minus k. Then we have to define L equal to 0 and R equal to 0 for 2 pointers, and this kind of sum equal to 0, and then we can find the minimum sum. We can define the minimum sum as initialized as the maximum one. And now we traverse the array, use R pointers and keep the left pointers fixed in the beginning, and then we add the card points value here. If the R minus L plus 1 is bigger than the window we need, then we have to shift L plus 1, and also we have default shift we need to minus the card points for the L position. And if they are equal, that means that we have found a possible candidate. So we have to update the minimum sum. And we add R every time to shift R. So then we return the current sum of the card points minus the min sum. So for the sliding window solution, this is the common pattern. That is, first we continues to add or multiplication something at the point with R pointers, and then if we arrive the or get the maximum windows that one more bigger than the certified windows length. We consider to shift the air pointers and also to minus the cut points at air position. And if the windows is that exactly what we need, we update the answer. And here we can add some corner case here. Even the question doesn't have a strings wiki. I think it's a good habit to add some corner case. Okay, another is if k is bigger than n, we should return sum of the cut points or whatever, or 0. Maybe we can return this one. It's for another corner case. Okay, we made it. Thank you very much for watching. See you next time.